last comment, but Raymond Ehlers, you'll talk about some future ideas for jet substructure measurements. Thank you.
Thanks a lot. So yes, first of all, thanks to the organizers for giving me the opportunity to speak here today. So I'm going to try and cover just some ideas about future jet substructure measurements with of course, the perspective that I have as an experimentalist and building in things that we've been working on. So already, I mean, Laura just gave a very nice overview, and we've had some other very nice talks already for during this workshop. We've really seen we have this very large collection of jet substructure measurements, right, also covered by Ray and Martin and honestly many others here, right? We could include most of the folks here. So to me, from my perspective, I'm a bit of an optimist, and I would say we still, of course, have some work to do, but I think we're making really great progress in terms of trying to add to all these different observables and trying to add to our picture here. So in particular, I think we've really made quite some improvements in terms of our understanding of our splittings, for example, our mistaggings experimentally, understanding the details of all this, combined together with kind of understanding our backgrounds and these different features. Kind of putting all these pieces together, and this, along with this grooming, this is giving us the opportunity to kind of unfold some broader classes of observables and opening up our phase space and our Loon plane. We've now seen this so many times. We can have our constant values and our delta R, our Z, or KT. We can make these different selections. Okay, catch up. These different selections. And by doing this, we can kind of move around our splitting phase space. So in terms of kind of trying to understand this, okay, we've just had our discussion here, so I almost don't need to say this, but just to put us all on the same page again, right? We see this. We see a little modification in our kind of our ZG measurements shown in the middle here. And we also see this kind of narrowing effect, as we've been discussing in these various observables. I have the Elise RG here on the right, right, but we've seen this in many other places, and it's well described, at least by a number of these models here. So as we've discussed here, we have this, whether these some coherence effects or changes in the quark-gluon fraction or combinations of these, we clearly are still discussing, but the point here is that I want to at least kind of trying to take these into account to see if we can try and make a more complete picture as we move forward here. So kind of in terms then of looking towards these future measurements, there are kind of three pieces that I'll try and discuss today. So one, I'm going to discuss a few select recent measurements, building on things we've already kind of mentioned here, using them as some examples to think about where to go further. Some extensions kind of just smaller additional steps to kind of existing measurements that we've already been working on, as well as then comment on some future directions. So by way of kind of recent measurements, I'd like to talk about this idea of trying to constrain the medium structure via jet substructure and trying to use this groomed observable also broadly kind of to talk about some of the experimental considerations we have and how those might drive some of the considerations we make as kind of we go forward. So okay, this has already been discussed at least conceptually here by many folks, starting with Marta on Monday. So the idea here is trying to kind of look for this Moliere scattering in the medium through our jet substructure. So go into this high KT tail and seeing if we can see this in our groomed jet substructure, kind of from the experimental side, thinking of this kind of maybe overly simple cartoon here, but as a complementary approach to trying to search for this via jet deflection. Great. So in terms of how we try and actually go about this extracting this hardest KTG, we're doing some new things here compared to in this kind of new set of measurements. So one of the things we've worked on here is trying to really kind of directly select our hardest KT splitting by utilizing this dynamical grooming approach. The idea here is that it's a way to kind of groom scaling based on the jet properties, and we can change this different hardness measure. So if we're trying to really select our hardest KT splittings, then focusing this measure, say for example on this KT measure, may give us the opportunity to more directly access these particular set of splittings, or more successfully access them. I will say a little bit more about this, but you should also certainly pay attention in Adam's talk, where I'm sure he'll go into this in much more detail. In addition to that, we also take this approach from that we've been doing quite frequently, using soft drop with the Z cut of O2, and we can make comparisons here then of kind of what these different grooming methods are looking at. Now, in terms of actually trying to make this measurement, which is relevant for KT, but also for a lot of the rest of these groomed substructure measurements, right? Experimentally, we really need to focus on two particular pieces, which is one, kind of trying to ensure we have sufficient subleading subjet purity, such that we are really actually able to unfold these measurements. And then secondly, is to try and deal with off-diagonal components in our response, which again, if we can't make this correlation, we can't unfold. So as the first step then, in terms of trying to understand our subjet subleading purity, we have this nice plot on the right from James and Mateusz, showing studies of this, again, the subleading subjet purity. So we need to do a matching in our, when we go to an unfolding between our true level and our measured level. And we need to do this both for both of our prongs. So our leading prong, this matching is always very high purity and doesn't cause us any problems. But the subleading one can be lost in many different ways. You can lose it outside of your jet. You can misidentify what it is. But in the end, you can classify this in many different ways. But in the end, you really need to just somehow find a way to have sufficient purity. In addition, then, to be very explicit, then we need also to deal, for example, with these off-diagonal components. So in terms of how we deal with this in the KT, particularly for using dynamical grooming, because it adjusts this hardness measure, we have some susceptibility to kind of softer Z components that, for example, aren't included in our soft drop measurements. And so because of that, then, as we saw on the last slide, then the purity of the subleading subjet can start to kind of suffer some. And so what we need then is a mechanism to deal with these mismatched splittings, which are a big component at a minimum at low KT. And by doing and to get to this for the minimum for the hardest KT, we in fact just end up imposing a minimum KT requirement. And so this has some costs in terms of our purity and kinematic efficiency. So I have these little cartoons on the right, and I mean, it's all schematic, but basically the point is, if you impose some minimum KT requirement to try and deal with these, especially soft splittings, you are able to substantially improve your purity, but at the cost of your kinematic efficiency. So you have some sort of optimization problem that you then have to work through to try and figure out how to actually be able to unfold this experimentally. Now, we do at least get a little bit out of this, which is if you look at the response in the KT, the largest off-diagonal components are very, very soft. And so again, this minimum KT requirement gives you the opportunity to deal with the off-diagonal components as well. So somehow this serves as a similar requirement for the minimum Z requirement in our soft drop, but gives us a somewhat different way to go about doing this. Still using these dynamical grooming algorithms. So with all that being said, then we can look at this, and we have these very recent first measurements using dynamical grooming in lead. So in the case here, I show for as a function of this KTG using this dynamical grooming with A = 1, this hardness measure related to the KT. And we see here the consequences of imposing this KT cut means that we have we're only able to go to this high KT region, but given our interest in trying to look for these molar scatterings, which we expect to show up at this high KT range, this can still give us some insight into the splittings. Excuse me. So we can do this for these different splitting methods, or for these different groom methods to make the comparison. So somehow what we've seen is that really you end up making the selection of the same set of splittings, at least in this region where we have the overlap. but then we can additionally, so if we then go back to our soft drop here, we don't have to impose this minimum KT requirement because it's taken care of by our Z cut, which then allows us to try and cut into to unfold over a larger KT spectra at the right, because we have a different way to address our backgrounds there. And so this has already been shown, so maybe I shouldn't, so I'll be brief, but basically what we see is that at least in comparison to the Hyman model with and without these molar effects, we're not, unfortunately not quite sensitive to kind of the differences between them, at least for this particular observable. So, right, so I went through this in a little bit of detail because it gets at least what we kind of need to think about experimentally, particularly as we try and address different, if we think about different approaches, we might try and take substructure, particularly with respect to grooming. So one can think of what one might try and do if one wants to expand this. So one being, you could try and imagine a modification to dynamic grooming to try and enhance this KT range. See if you can reduce this minimum requirement, for example, by trying to incorporate maybe some hybrid or some combination of a Z cut. Or you can also just try and move to harder KT, where your cut into your range is less significant. So in particular, right, one can think, for example, about this Atlas D12 measurement here, right, which is again getting at this KT, but in a very different kinematic range. So I'd be curious to, so you know, the entire Atlas measurement really fits into kind of this near this single bin. So it'd be interesting to see how one, if what comparisons might look like for with molar on and off in terms of the models, to see if there's more sensitivity here. So then in terms of kind of going forward, then we've just discussed this, so I will be very brief here, but I think at least points at kind of another direction we can go in terms of trying to add additional selections on our measurements. It's kind of a next step. Okay, we had a discussion about what information this might actually add or not, but at least this we have this picture, and we can continue trying to expand what information we can try and select on. So maybe in terms then of kind of natural evolution of this, although I think quite difficult, would be thinking about trying to unfold the lumen plane in lead, and we've seen quite recently that we now at least have this under control in PP using this 3D unfolding, and then the jet PT, the KT, and the delta R. That, of course, being said, trying to unfold this whole phase space becomes, of course, very, very difficult, because you have all these different possible background contributions. So you really need very careful handling of your misidentified subjects, which I think requires some thought and perhaps some different approaches to our background subtraction. If this isn't possible for some reason, or for the reason being particularly this background, one could also imagine trying to try and extract some information based on 1D distributions, assuming they're not all entirely degenerate, by looking at something like a Bayesian inference and trying to constrain based on those different observables. So continuing then to connect with our discussion already, I want to keep thinking about this question of kind of what jets we're actually measuring. So Laura, I think, already described this nicely, and I think we're quite familiar with this now. But the idea somehow of having this survival bias, what we can do to try and actually access additional phase space in terms of right. We of course can select get at the initial energy in the same way, but as this deep learning approach perhaps, but we are losing some of our phase space then if we're only looking at these kind of narrow jets and seeing somewhat less of our modification. So the other way that I think about this in terms of kind of thinking of going forward is also understanding what we lose with these Z requirements, for example, in our soft drop. So here, this is from some nice predictions from Quark Matter from Zach, and what we see here, for example, on the right is again this KTG in this Alice kinematics, and on the top you have basically doing it with a soft draw, or I mean doing it with no Z requirement. On the bottom you see with a Z requirement. What you see is that by adding this Z requirement, you really cut into the differences that you might actually be sensitive to if you're comparing basically with and without the Moliere. So comparing the red to the blue. You see the same sort of thing, for example, in the RG, for example. And so somehow it seems to be a lot of these prominent Moliere effects, for example, are showing up at low Z, at least for this particular implementation with the hybrid model. So somehow it seems that some of the background requirements we have in terms of our for being able to make these measurements experimentally may be cutting to our kind of phase space of interest. And so together, to me, this kind of raises the question of whether we can try and access the rest of this phase space. So can we find a way to try and relax these requirements on our Z or our PT or our KT to be able to have some more clear signals in terms of observing these different effects. So can we find a way to do that while actually keeping our observables and background under control? So basically asking the question, are there some newer techniques we can apply experimentally, or perhaps are there some additional ungroomed observables? We've already seen some, for example, with the angularities to provide the opportunity to get to this region. So I think in terms of kind of a natural extension here, one can think about trying to do some sort of triggered or high flavor or heavy flavor substructure. So you find your gamma or your Z and try and make your substructure measurement with that tag, with again trying to access somehow this less survival biased distribution. Alternatively, one can try and look at, for example, your HF substructure. So this is, for example, looking at D-tag substructure for the ZG on the right, where we see some difference in the momentum fraction here, the momentum sharing fraction here. So trying to use these different tools to actually try and give us an additional lever for exploring our substructure observables, with the understanding, of course, that we need to deal with our statistics here as well as our background. And so as we move to kind of these future steps, this might be something that's more addressable. Something else to me that seems worth some investigation here in the near future is to look at this time reclustering. So the idea being that if we emissions aren't angular ordered in the medium, can we account for this in our reclustering, or what effect this might have? And so Liliana will talk about this a little later today, but the idea here is somehow if we modify our reclustering, instead using, for example, a generalized KT with this particular exponent of 0.5, if we're at least focused on our formation time, we might be able to access it more consistently, at least with a narrower distribution in terms of how we're able to find it. This doesn't have quite so much effect in terms of if you're comparing this time reclustering versus groomed Cambridge-Ogden. But again, if we want to try and relax some of these requirements, then this may give us the opportunity to. This also works better without grooming, so this maybe gives us the opportunity to kind of try and relax these considerations. As an alternative approach, then thinking a little bit kind of further along, I also think these energy correlators may give us a different way to try and look at the same problem. And the idea here is with trying to basically reframe jet substructure in terms of these correlation functions. So you're correlating this energy flow, and so I think you're getting kind of the same set of information, but in a put together in kind of a different way. So in terms of how I understand this, kind of the simplest is kind of this 2-point correlator, where you try and you're basically characterizing the separation between your delta R between your different jet constituents, and you construct this correlation by correlating them all together, weighting them, for example, by their energy, such that this will somehow then focus on your harder components in your measurement. So this has been done, for example, with the CMS open data, and this is shown on the right here. And so you have these different regimes in terms of kind of the relevant scales for QCD, where you have this kind of flat regime on the right for these larger angular scales, and then this more steeply falling phase on the left with closer separation, where your hadrons are kind of your more relevant elements. So this is of course quite new, and this is again coming from the PP side. So so in terms of feasibility, we still need to think about this very carefully in terms of whether this is really feasible for heavy-ion collisions. And in particular, we need to think very carefully about how we would actually unfold this. But I think it at least points to a different direction to kind of try and get to some fundamental information and look at how it might be modified. Now, in terms of just as an additional thought here, this is this energy correlator, for example, the ungroomed observable. So we need to have a very careful treatment of the background, somewhat different than what we've done in our groomed substructure observables. And one thing we can think about doing, I think probably all of us have seen this slide at some point, but is to think about trying to utilize this idea of using the mixed events to construct our background for these ungroomed observables. So the idea being basically you take components of similar events, or like a single track from each event, to construct these mixed events that then will describe your background very effectively, but preserve your signal of interest. So this has of course been used in STAR, for example, with this plot on the right showing the yields. And I will leave this to Peter to discuss in detail, but it requires some careful thought about how to actually to construct our observables so that this works effectively. But this might be something that we want to consider trying to employ in substructure to kind of continue to push the phase space that we can measure in. Lastly, as I kind of come to my close here, we can also think about trying to employ machine learning in different ways to try and improve our ability to make these measurements, or what observables we actually make. So one being to for example, trying to think about extending this ML-based background estimator for jet substructure. One needs to be very, very careful about how you do this because the way the estimator is constructed depends on the details of the jet and the constituents. So one needs to be very careful about imposing an additional bias. But this is, I think, at least worth thinking about, as well as this ML-assisted observable design from, again, James and Mateusz and collaborators, where, for example, you might be able to construct some substructure-based observables that are more sensitive to modification, with the bottom two here being based on these energy field polynomial or n sub jettiness. But I think Mateusz will talk about that in the next talk, so I will leave that to him. So coming to my kind of summary and outlook then. So I think, again, I'm an optimist, but I think we've made quite some progress here in terms of making advances in our jet substructure measurements. I think we've kind of moved to systematic, or to kind of comprehensively try and study, at least in terms of our green substructure observables, and we're moving to add more to more differential measurements quickly. I will point out, of course, there are many important ungrouped observables that I didn't cover here. There's just, I think, too much to talk about, but it's important not to forget about these pieces as well. In terms of where we might go, I think trying to think about relaxing some of these cuts and selections to try and move into the broader phase space might be something of interest as we go forward, as well as these different new techniques, many of which I at least tried to discuss. So then, in general, I would say it's important that so I've tried to highlight these things, but we of course shouldn't forget that we want to continue really exploring and filling the phase space that we have, right, we can expand, we can take our existing measurements and try and expand, for example, our PT reach or in different variables to really make sure that we can comprehensively constrain models as in a broadest phase space as we can. And I think looking forward, I think things look really quite interesting with as Phoenix coming online and LHC Run 3. I think we'll continue to see really very interesting measurements coming out of both RIC and LHC. Thanks.
Thank you very much, Raymond, for a very nice talk. We have a question from Adam.
Hi, thank you for the nice talk. So in the beginning of your talk, you had this slide of the groomed transverse momentum. And I was curious if you...
Sorry, it's slow. Yeah.
So I was curious if you have studies with other Monte Carlos, because I think it would be, for example, interesting to see what Lido or Jetscape would say for the same observable, because there is this suppression of large KT, enhancement and small KT. And I kind of feel that there is a possibility that even though they will all describe this suppression and enhancement, probably the transition point or the slope of the transition is different in these models.
Mm-hmm. Yeah, I think that's something we're very much interested in doing. This was a little serendipitous, let's say, which is, we're in the process of collecting some more models to make precisely this comparison. So yeah, very much agreed. That'll be interesting to see.
Okay. Question. I thought I saw something. Yeah, I think first there.
Could you go to slide 10?
Slide 10.
Sure. So this is an honest or maybe dumb question, but maybe both. What is RG true? I mean, at which level is that defined? Is this at the hadron level in Pythia, or is it at some attempt to actually look at the parton shower?
Yeah, so this correlation should be between the embedding and really the Pythia true level, so not detector level.
But what is the true level in Pythia? I mean, at the hadron level, or?
Yeah, at the hadron level, yeah.
So then I have a follow-up question, but maybe not directed at you, but I was just curious. Ages ago, there was this rapid response workshop at GSI, which some of the people here attended, where there was an effort started to look at the correlation between the hadron level observables and the actual shower evolution in the generator. To see to which extent whatever you measure is actually related to what happens even with a perfect detector. And I don't know that I've seen a lot of reports on progress on that particular question at this workshop. So I'm wondering if, okay. I thought that was very interesting, but it seems to have fallen off the radar a bit.
Mea culpa. So.
Gunther, I think that was targeted at several people in this room, myself among them. So there was an attempt to write it up, but it's a complex thing. So I think it was a good start, but needs some more work. So Raymond, I'm going to pitch you a softball, and I don't want to step on Yi's talk tomorrow, but if I just take a step back from the details of your talk, it's a series of one-dimensional plots of models and data, and largely things agree, but heavy ions is by its nature a high dimensional multi-messenger thing. So what are the prospects for doing that? I know you have an answer, and I want to ask it from the experimental point of view. Do we understand our uncertainties and our covariances, the uncertainties to the necessary degree to really do a true multi-messenger analysis? And if not, what do we really need to do?
Yeah, thanks for the softball. So I mean, right, we're hard at work at trying to do precisely this Bayesian analysis in the hard sector in Jetscape, and in terms of to try and answer precisely your question, in terms of kind of the uncertainties, I think this is still a work in progress. So this is, I think, a good reminder to say, you know, to really try and extract this in a precise manner, right? We need to understand the correlation between the different uncertainties. And so even just reporting, for example, sign uncertainties can make a big difference in our ability to really accurately understand these in terms of this Bayesian analysis. So, I mean, I think, yeah, certainly, I think this is a topic of interest. Getting to these substructure observables, I think will take a little bit of time, but I think, yeah, certainly, as you say, with these different 1D correlations or 1D observables, it gives us the opportunity to try and extract some more information from that. So I think it's work in progress, but going in the right direction.
All right, guys. Thanks for again to Raymond for a very nice talk.